Hey guys, what's up? Today we are going to learn about the analysis of a building frame using SAP 2000. And so I'm using SAP 2000 version 14. And in this tutorial, we'll learn about a building frame. Specifically, I've taken a problem from the book of K.M.Leet. It's page number 224, question number 56. And this in this question, the frame is a two-storied building like this, in which the left part of the frame there is a load of 0.8 kips per feet. It is a wind load. So we are going to analyze this frame, and the thing in this frame is the columns, the vertical ones. There are four columns, that they are A, B, B, C, D, E, and E, F, and their properties are given, like the moment of inertia is 640, area 17.9, and for the girders, that is the horizontal ones, there are two girders and their moment of inertia and area is different than that of columns. So the problem is, like, we have to find the deformation or the displacement of joint D, and the question says that it shouldn't be more than 0.4 inch. So we are going to analyze the frame as a two-storied building, as a two-storied frame, and we are going to find the displacement of joint D. If it is less than 0.48, it's okay, it is safe. And but if it is greater than 0.48, we are going to introduce a bracing, AE, and this will be included in the second part of the tutorial. So for the first part, we will just analyze a two-storied frame without bracing. Okay. The first step in the analysis of any civil engineering structure is to define the grids. So to define the grids, and let's click on File and click on New Model. Then we can see a template, and this menu which shows a number of templates for beams, trusses, and frames, 2D and 3D frames. And there is one option called Grid Only. So all of these templates are made from this option. So if we know this basic thing, then we can work in all these templates. So I'm going to just click on Grid Only, and it asks us to enter the number of grid lines in the x direction, y direction, and z direction. So I'm going to take you to the problem. In this problem, we can see that in the horizontal direction, and the distance is 30 feet. Now the spacing between two columns is 30 feet, right? And in the vertical direction, the first story is of 16 feet and the second is of 15 feet. So the first thing I want to tell you is that in general, uh, we use x-axis as a horizontal axis and y-axis as vertical axis, right? But in SAP, the default axis direction is x and y are considered as horizontal, and the z direction is considered as vertical. So for this problem, I'm going to take x direction as horizontal direction and z direction as vertical direction. So we are not going to deal about y direction because it is a 2D problem. So the other thing is to find the number of grids. We just have to think about the graph papers. It's like how many lines are we gonna need to design or to draw this thing on SAP, right? So we need two vertical lines, reference lines, right? And three horizontal lines to draw this structure. One to join AF, the other to join BE and CE. They are just the reference lines. They are not the actual structure. We are going to draw the actual structure on these things. Okay, so I need two vertical lines. That means I need two grid lines along x direction. Okay, along x direction I need two lines, and I'm not going to consider y direction because it is a 2D problem. So is a vertical direction. The SAP always takes z direction as its default direction. So make y direction as 1. okay, and along z direction, the vertical direction, in this vertical direction, the number of lines that I need, the horizontal lines that I need is 3, right? 1, 2 here and 3 here. Okay, uh, there is one thing that you may be confused, because you may think like there is no girder in here, so why are we gonna need three grid lines, right? Making three grid lines will help to locate these points A and F. Just note this thing that the grid lines are not the real structures, they are just the projection line. You may either draw your structure in them or not, it's up to you, it's up to your model. Okay, so you will be more clear in upcoming um, video. So I'm gonna just there, so there are two grid lines along x direction and three grid lines along z direction. That's it that you have to understand for now. Okay, so about the spacing, I will just edit them in a little time, a bit later. Okay, so just press OK. Yeah, you can see it, this is the 3D view, right? It's written at the top, right? 3D view. So the 3D view of the 2D objects looks like this. Okay, and in here I'm just seeing a line. It is because the view is xy plane. Since we are working on x and z plane, I'm going to click here xz view. Okay, yeah, this is the grid line and I'm going to draw my structure over here. The grid lines um, should be like that. You can draw your model in here. So yeah, by looking this uh, grid lines and the model in my problem, I can say that I can draw my model in this grid line. Okay, so the first thing you should do is make your units like that you need. In this figure the units are in keep and feet, right? And so look, the dimension are in feet, the loading is in keep, so I have to change this thing, so it is keep feet. Yeah, we shouldn't forget this thing because it will mess everything at last if we just forget changing the units. Okay, now right click on your mouse and I get this menu and it says that edit grid data. Okay, so I'm going to modify this global system. Okay, click. So there is other basic thing that I have to teach you. So there are two ways I can put the coordinates or make the models dimension, insert the models dimension. So the first thing is through ordinates, right? So uh, a is a line along the reference line, it is a grid line along x grid data. Okay, so a is this line, just consider it as this line. Okay, and b is the other horizontal other vertical line. Okay, so the distance of a from this axis origin, this is the origin, right? So the distance of a from origin is 0, right? It is already 0, so enter. And b, it is 30 feet away from origin, right? If this is this point, if this point a, joint a is considered as origin, so this column is at distance 0 and this column is at distance 30 feet from a, right? Okay, so I'm going to use 30 feet and enter. Okay, I'm not looking at y grids, so I'm going to z grids, and in z grids um, the z1 is this horizontal line and z2 is this horizontal line and z3 is this horizontal line. Okay, so the distance of z1 from origin, it is 0, right? So press OK, and the z2 is at a distance of 16 feet. Yeah, 16 feet. So type 16 and enter. And the other one, the top one, is at a distance of 16 plus 15 feet from bottom, right, from origin. So it is 31 feet. Yeah, 31 feet, right? And enter. Okay, that's it. And the other way you can put the values or arrange or edit the grid lines is through spacings. In here, click on spacing and look, the spacing, it says that the distance between these two grid lines spacing is 30, right? We should write at the top. And so there are only two grid lines, so there is only one entry. And in here, the spacing between Z1 and Z2 is 16 right here, Z2 and Z3 right at top 15, and there, since there is no other grid line, so it is 0. Okay, so it's easier to work with ordinates if you are a little bit confused about spacings. So then click on OK. Okay, and right now I can see that my model, my grid lines, it is bigger than the windows. So to make its size adjustable, or mm, that can be inserted in this window, is through this option. In here it says that, yeah, to restore the full view, just click on this option, and yeah, all of this thing, this object is inside my window. Same for this part, so restore full view, and that's it. The other thing you may be confused is there are two grid lines along x-axis, right? Since x-axis is horizontal, you may be confused that why are grid lines along x vertical. So the grid lines are the lines that are perpendicular to the axis. So the grid lines along x are the perpendicular lines, and the grid lines along z-axis are also the perpendicular lines to z-axis. So these horizontal lines are perpendicular to z-axis, and these vertical lines are perpendicular to x-axis. So always remember, grid lines are perpendicular to the axis. Okay, yeah, that's the thing. Okay guys, now we are going to define materials for this frame, and we look at our problem, and it says that the columns and the girders are made of a material whose modulus of elasticity is 29,000 ksi. So we are going to define this material in SAP, and for that we'll go to define materials, and there are two materials, default materials that SAP uses, but we are going to add our own material, and for that we'll click on add new material, and I will name my material as new. And since the girders and the columns are made of steel, so the material type is steel. It can be concrete, aluminum, and other things as well. So I will change the units in here. It is for 29,000 ksi, I should put it in keep inch. Yeah, so it shows that the value is 29,000 ksi, the value of E. So for steel, the Poisson's ratio, it is 0.3. We don't need to look at any other values for the analysis part of the frame. So I'm just going to click on OK. I can change the color of the materials, and it is blue for this instant. If you click here, you can put your own material color. So okay, click on OK, and this is here. I can see my material new, and it is being made. Okay, then click on OK. So after defining the materials, we are going to define the sections. And about the sections, the problem says that the column has a moment of inertia of 640 inches to the power 4 and area of 17.9 inches square, and the girders have different moment of inertia and different area. So what we are going to do is we are going to make a different section for column and a different section for girders. Okay, So let's make a section for column first. So go to define section properties and go to frame sections. Okay, so I'm going to add a new property. Yeah, since our problem doesn't say specify a particular type of standard section, so I'm going to define it by my own. So go here and click on other. Okay, so I'm going to design a section, so click on section designer. So I'm naming it COL for columns, and the base material, select the one we just made, so it's new, and I'm going to click on the section designer to design my section. Okay, so click on this rectangular part, it says draw solid shape. Okay, then I'm going to click at any mm, mm, part of this window, just click. Okay, then you can see that there is a rectangle, there is a square formed, a section formed. So right click on your mouse and it gives some properties, shape properties, right? So it says name is rectangle, so I'm going to change, I have to change the material. In here it says it is 4000 psi. I'm going to change it to new. Okay, click on new. Okay, so I'm going to press OK. Now the other thing is, in our problem the units are given in inch to the power 4, are given in inch, right? So I will make it in inch. It is in keep feet, I am going to make it in keep inch. Then I'm going to display show section properties. Okay, so in here it says that the base material is new, we don't need any other values uh, for the analysis part. So look at this thing, note this area that is made by the software as its default value. So the area is 576, and the moment of inertia, there are two values, right? But they are all same, so just pick 27648. Yeah, it is same for both. These are the moment of inertia along 2 direction and 3 direction. They are the local directions, and the area is 576. So just note down this area and moment of inertia in your copy or somewhere, so so that we can modify this thing. So just press OK and click on done. Okay, now I'm just click on the set modifiers, property modifiers. Okay, click. Yeah, so the thing is, the area shown by the software was 576 inches square, right? So I'm going to change 576 to the required value, which is 17.9. So to change that, I'm going to use a modification factor, a multiplication factor, that will convert 576 to 17.9. So there is one thing I need to tell you, that every box in SAP acts as a calculator in itself. So if you want to do any calculations, you don't have to use your calculator. So you can use these boxes. So to use them, just press shift and press enter, shift enter. Okay, so there is the calculator. So my modification factor will be the value that I want is 17.9, right? Yeah, 17.9. So the value that I want, 17.9, divided by the value that is given in the software, that is the default value, it is 576. Okay, so calculate. So this factor is 0.003, 0.031 is the factor that will convert 576 to 17.9. So the thing is, this thing is going to multiply with 576, right? So the net result will be 17.9. So the area will be 17.9, right? So calculate, just click OK. So sometimes the windows gets closed after showing that error, so it is better to save your work while you are working so that it is not lost. Okay, so I can see here this term, yeah, when it is, this is the multiplication or the modification factor, it's in the power minus 2. Okay, so now click on OK, and for this section you can choose your color. The default color is white. You can make it any color by clicking here, so you may have red, green, anything you want, but don't make black because the background of the window is black. Okay, so just press penciler. Okay, let it be. Yeah, okay, and okay, so what I'm going to do is save my work first. Okay, save as learn. Yeah, I'm going to make a folder SAP. Okay, make a different folder because there are number of files attached to one SAP file, so make a different folder for each one. So frame analysis. Okay, save. Yeah, just save it while you are working so that you won't lost your work. So what I'm going to do is I have already defined section for column. Now I'm going to define a section for girders. And for girders, the moment of inertia is 800 and area is 11.8. So I'm going to use the same thing, the same process. I'm going on section properties, frame sections. Yeah, we already have section for column in here. So I'm going to add new property, and yeah, it is others already. Go to section designer, and this is for girders, right? Girder. And I'm going to choose my base material. It's new. So section designer, and what I'm going to do first is change the units to keep fit. Okay, and click on this part. Just click anywhere on this window. It will give you a rectangle, and just click on your uh, mouse right button, and you will get material. Change the material to our own material that's new that we made, and just click OK. Alright, so go to display and look the section properties. So I'm seeing the same values in here. The default values that SAP uses, it is 576 inch square for area and 27,648 for moment of inertia. So note down these values. I'm going to use a modification factor that will mm, change or make our desired area. Okay, so done, and go to set modifiers. For the cross-sectional area, I'm going to use the inbuilt calculator to formulate that modification factor. So press shift enter, and you'll get the calculator in here. So the value I want for area is 11.8. Okay, 11.8 divided by 576, right? The default value. So when it is good, this factor is when going to multiply with 576, the net result will be 11.8. That's the simple math. Then press OK. Yeah, there is no error this time. Okay, then click on shift enter, and the same thing for moment of inertia for girders 2. The area we need is 800 divided by 27648. This is the default value. So calculate. So let me confirm the moment of inertia. Yeah, it is 800 into the power 4. Okay, so press OK. Yeah, and the same thing for the other part. Just press shift enter, and it is 800 divided by 27648. Yeah, calculate and press OK. There is error this time. Maybe it will kill our work. Yeah, this thing happens a lot. Cancel this thing. Okay. So I've already saved my file. I'm going to open that one. I'm going here and in learn. As I said earlier, this error occurs for a number of times, so you should save your work. And here it was saved. Okay, I will open this file. Okay, it's opening. It will take a bit time. Okay. Okay, I'm going to check if my sections are present. So go to section, define section properties, go to frame sections. Yeah, the column is survived, but not the gridded part. So I'm going to add new property and click on other. It's pretty boring, but okay. Gridder. Here go to new and section designer. Okay, so click here. Just click on any part of the window. You'll get a rectangle or a square. So firstly change the units. They are already in keepings. That's okay. And uh, right click on your mouse. So change the material property. Don't forget to change this thing, because otherwise you will get a different result, because we should use the material that we made. Okay, so new is the material that we made, and click on OK. Go to display, show section properties. Okay, then the area is all same. The default value, they are always same. So click on OK. So done. So the thing we have to work on is modifiers. Sorry. And in here I'm going to use calculator again, so shift enter. So in here thing I need is the area 11.8. 11.8 divided by 576. Calculate and click OK. Yeah, so in here shift enter, calculate this part. The moment of inertia we need is 800 divided by the value that is given here, 648. Okay, so okay, yeah. To avoid the error again, just copy this factor, Control C, Control V. Yeah, okay, it will work. Press OK, and let's change the color of this section, make it red. Okay, girders. Okay, the section is girder. We've used the material, base material new, and we defined or made the section through section designer and used modifiers, yeah, modification factors, and I used the colors. That's the thing, and this is it. Click OK. So I can see that there are two columns in here, two sections in here, one for column and the other for girder. So that's what we need, and I will click OK. Now I will teach you how to assign these sections to each member. Okay, so in this part now I have to draw the structure like that given in the quick problem, like that. So to make that, click this part. It says that draw frame or cable element. Just click on that. Click OK. So if we are making a frame or and a beam, then in this part moment releases, there are two options. One is pinned and the other is continuous. If you are working on truss, then always use this option pinned, but for frames and beams, always go for continuous. Okay, so if I used pin, so there won't be moment at the joints. That is the case for truss, right? But in frames we do have moment at the joints, so I'm going to use continuous. So the other thing is the sections. It says that the section are column, so there are two sections and the other says none. So we are going to use either column or girder. So let's draw columns first. Column, right? Then I'm going to click here, from here to here. I'm drawing columns. Enter. Okay, so to draw the girders, I'm going to choose girder. mm, from here to here and escape. Click again for girder, here to here and enter. Okay, so choose column, here to here, from here to here, enter. Yeah, that's what we need, right? And it looks like our actual model that's given in the problem, right? Yeah, just look at the grid lines in here. So there is a grid line, but we haven't drawn our model in that part, so either we use or just leave the grid lines, so grid lines won't matter much. Okay, so there is nothing to be confused about the grid lines. Okay, so now uh, if I want to look at the name of the sections, then I'm going to click on view, and there is an option set display options. Okay, so for frames I'm going to click on sections, right? So okay, click OK. So it says that the section used in here is COL, column, 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 and on this part, the horizontal parts, it is girder and girder. That's what we did, and that's what we want. Okay, as a next step, we are going to assign the joints to this frame. So in our problem, there are two pin joints. Okay, at joint A and F. So to assign the joints, go to assign. Before that, click on the joints where you want the supports. Okay, since there are same pin joints or supports at this point, so we are going to assign the supports at once. So click these points, then go to assign and joint and click on restraints. Okay, so there are options like internal hinge, roller, this is pin support, this is fixed support. Since we want pin support, I'm going to click on pin support, and or we can just select from here, like in pin support it will restrain in all three directions displacement, so but the rotation will occur. So it's like that. If it was fixed, then it will be restrained in all six directions. Okay, but in our case it is just pin, so click on the support and press OK. So now you can see that we have assigned pin supports at these two joints. Okay, after assigning supports, now I'm going to teach you to define load pattern. In our problem, the question says that the load acting on this structure is due to wind load of 0.8 kg per feet. So the load case may be different, like sometimes you have to analyze for the dead load of the structures, and sometimes it could be wind load or live load or other kind of load. Okay, so in this case in this problem we are going to deal with wind load. So I have to define that pattern, specify that it is a wind load. Okay, so go to define, and there is option load pattern, right? Just click on load pattern. So there is already one option for dead load, so I'm going to make one pattern for wind. Okay, so in the type just click on at this point, and we see that there are several cases for live load, earthquake, wind, and others. So it is a case for wind. Just click on wind, and after that just click to add new load pattern. Okay, yeah, and here we can see that there is one dead load and other is the wind load. We don't need dead load, we are just going to analyze for wind load, so let it be. We will just select wind load at the during the analysis, but right here it doesn't matter even if dead load is present or whatever. Okay, so just click on OK. After defining the load pattern, I'm going to teach you to assign the loads to the system. In our problem, it says that a load of 0.8 kg per feet, it is a uniform load, uniformly distributed load is acting on the left part of this frame, right? So I'm going to assign that load. This for that I'm going to select this column, these columns both, and go to assign, and in here there is one option called frame loads, and there are different kinds of loads like gravity loads, point load, and distributed, and for right now I just want distributed load. Okay, so in here it says that the load pattern name, so our load pattern name was wind load, right? So click on this part, in here it is wind. Okay, so let me change the units, make it keep feet, because the load given in here is 0.8 keep feet, right? Okay, so and the other thing is the direction of this loading is along x-axis, along positive x-axis, right? Yeah, from left to right it is positive x-axis, so it is plus. So the direction of the load is gravity, it's not gravity, it is not downwards, it is to the positive x, right? Okay, so the direction is x, and the load is uniform load, it is 0.8 keep feet, right? So we must change the units. So in here in the options it says add to existing loads, replace existing loads. In the problem, in our problem, there is only one load, only one distributed load, so it doesn't matter actually. You can click on any other options as well, any options add to existing load, since we don't have any existing load, so you can click here, either replace existing load or delete existing load. You can click on any of these for this part of for this problem only. But if there were several cases of loads, then we have to look at what we want, so the case will be the scenario would be different for that part. But for right now, it is just a uniform load of this, and you can click on any options you want in here. Okay, so and this part of the load is for trapezoidal load, mean that the load, either if the load is triangular or trapezoidal, then I have to use this one. I have to fill these boxes, but right now I just have a uniform load and it is 0.8. Okay, so it is a force along x direction, and then click on OK. Yeah, we can see that the load is uh, but the load is showing a bit different. It would be because of different unit in here, keep inch, it is in inch, so let's make it keep feet. Yeah, so it's showing 0.80 keep feet. Okay, let's check in here. Yeah, it is 0.8 keep feet, keep per feet. Okay, so this is how we assign loads. After assigning loads, the last part of the analysis is to analyze this frame. We have defined the material, we have defined the sections, assigned them, and after that we have made a load pattern, and assign load in this frame. So the next step is to analyze this frame and look the shear force, bending moment diagram, reactions, and deflection and deformation of this frame. Okay, so to analyze this, just go to analyze, and in here it is run analysis. Okay, so there are several options. It says model option there and several others, but and it is showing that the action is they are all going to run. So I don't want any other load to affect my analysis, so I just want the analysis to analyze the wind load. Okay, so I'll, for this part, I will just click on this here, run or do not run all. Okay, it will make do not run to all the load pattern in here. So uh, they are not going to run if I just made run now. So I just want this to run. So to make just this wind load to run, I'll click here, run or do not run case. Okay, so click here. So it can make run or do not do just single option, right? So I'm going to click once and make it run. And now since my only load is wind, so I will run now. Okay, it will take some time, and after that you will see a deformed shape of the frame. Okay, yeah, in here in the left part of the window, yeah, I can see that the frame is a bit deformed, right? So I have to find the deformation at this joint, and it is already showing that u1 is 0.232 feet. It is showing in feet, so I'll convert the unit to inch. Sorry, so it is 2.7845, and our problem says that the maximum deflection that is allowed is 0.48 inch. So the structure is unstable. We can conclude that. So we need to introduce bracing in here, right? This is how we know the deformation of joint D. Okay. So to see the shear force diagram and bending moment diagram, we can click here. So forces or stresses, click here and go to frame. Okay, and our load is just wind load, and I want to see axial force. Okay, and in here make the scaling auto, and I want to show the values on the diagram, right? So click on OK. Yeah, this is the axial force diagram. You can screenshot it and print it and just look at the values. Okay, after that, if I want to look the shear force diagram, I'll click on shear 2 for shear, go for 2 and for moment go for 3. Okay, just click OK. This is the shear force diagram, and to look the bending moment diagram, go to 133 and click on OK. Yeah, this is it. This is how we prepare shear force and bending moment diagram of any structure. Okay, if I want to look the deformed shape, how is it is it deforming from the original position? I'm just going to click on this part, and it will show deformed shape, and the load combo is just wind, and the scaling is auto, and also click on this part. Okay, wire shadow, so it will also show the original position of the frame. Click on OK. Yeah, the original one was this white one, and the deformed one frame is this one. So it shows how is it deforming, either it is showing left or right. Okay, uh, the other thing is, if you want a table for the deformation of each joints, then you can go to display, show tables. In here go click on joint, mm, and click this one, click this one. Yeah, if I want to see the joint displacement table, I'll just click select this part displacement, and in here select load pattern. I will just select wind and click on OK, and in here just wind. OK, and click on OK, and I will get a table, and it says that the joint 1 is displacing 0. It is true because it is pinned here, right? And point 2, the displacement is 2.16893. Yeah, it's like that. Okay. and and for so the nodes are like 1, 2, 3, 4 and 5, right? So for 5 it is maximum and it is 2.7845 inch. So it is greater than that allowable, and the allowable value was 0.48 inch. So it is pretty higher. So we need to introduce bracing in our frame, and we can copy this table to Excel, and there is an option export current table to Excel. By clicking here it will move to Excel. Okay, done. The other thing is, since there are two pin supports pin supports, if you want to find the reaction for this frame, you can go to display, show table, and in here just click on reactions. Okay, unclick this part, and just select the load we want. Okay, select load case point. Okay, click on OK, and we can see that at joint 1, which is this part, the reaction is F1. It is along, it is the horizontal reaction. It is 14.89 horizontally, and at joint 6, F1 is minus 9.91, and the vertical reactions are 12.813 and 12.813, opposite, just opposite, equal and opposite. So the other thing I want to tell you is, if you are confused about uh, joint, which one is joint 1, which one is joint 6, 4, 5, then I'm going to tell you. Click on OK, done. For that, unlock your system. Yeah. Okay, so to identify the joint naming, just go to view, and in here set display options. In here it says label joints, right? So click on labels, and OK. Yeah, now we can see that this is joint 1, this is joint 2, it is 3, this is 4, this is 5, and this is 6. And that's how we analyze the frame. Okay, thank you. Okay guys, now I'm going to summarize what we did in the first part. In the first part, we designed this model which had two pin joints, supports at A and F in SAP, and we found the deformation at joint D, and it is 2.7845 inch, which is greater than allowed value, which was 0.48 inch. So we move on case 2, which says that if the bases of the columns at point A and F are attached to the foundation by fixed supports, just note this part, fixed supports instead of pin supports, how much is the lateral deflection at joint D reduced? So I will just change pin supports to fixed supports, and I will look at the deflection at joint D, and we'll compare the results of case 1 and case 2. Okay, so for this part I will just unlock my analysis. Okay, yeah, I'm back to So on okay, so I have fixed supports at these joints, so I'm going to remove them. Okay, just click these joints supports and go to assign joint restraints, and in here go to hinge. Okay, yeah, so I've changed my fixed supports to hinge supports, pin support once again. So right now I'm going to analyze it by introducing a bracing element from this point to this joint. Okay, so now, and for that I have to define the section for that part. The material I'm going to use the same because it doesn't specify a different material, and it says U is equal to 29,000 KSI, so it means that everywhere in this structure just steel is used. So the material property for this bracing element will be same to that of girder and columns. Okay, so uh, for the sections I have to define a section whose area is 4 inches square, and the other thing you need to know about brace elements is that it doesn't take moments, so we are not going to consider moment of inertia of this section, because the bracing elements are just for tension. They are just tension members. They will just take tension. They won't even take compression. uh, so mm, it will act as a truss, like a truss member, because it won't take any moment or shear. So the thing is, while making this brace element, I have to consider it as pin joint at both ends. Okay, but before that I'm going to define a section. Go to define section properties, frame sections. Yeah, we already have column and girder, but I need a new material property. So for other, go to section designer. Yeah, name it bracing, brace element. Okay, brace, and our base material is new. And go to section designer and click on this rectangle and click anywhere. So previously we did like made a section and just changed it or convert it to the required values by using a modification factor. There is one other way we can uh, work out. So I'm going to teach you the other way for this case. And so just right click on your mouse and change your material. It is new, right? Okay, so in here it says that in our problem it says that the um, bar is 2 inch by 2 inch, right? We don't need moment of inertia in this case, so we are just dealing with area for bracing element. So I'm going to change in here, but before that okay, height, it is 2 inch, it is 2 inch, right? The unit is keep inch, so it will work. So it says 2 inch by 2 inch, the area is 4, 2 into 2 4. Yeah, it will work. So since it is a brace element, we don't need to modify moment of inertia, we don't need anything related to moment. So the height and width are 2 and 2, and the area will be 4. Okay, just click on OK and look at the section. Yeah, the section seems to is too small. We don't have to care about that. Just go to display and look the properties. So in here it should be 4. Yeah, it is 4, and we don't care about the moment of inertia. We don't need it for a bracing element. Just remember that. Okay, so the area is 4 and it is in inch square, right? It is in inch. Okay, click on OK. So done. So we don't need to modify uh, this area because we have already got area is equals to 4, so I don't need to modify that area. That's the value what I want, so it should be 1 in this case, not lesser than that. Okay, just click on OK. So, and as a color I'm going to use it green. Okay, click on OK. So we can see that there is other section named as brace, so I'm just gonna click OK. So to draw that element I have to click on draw frame or cable element. Okay, so in here now I'm going to make it pinned because it is a brace element, so the moment release will be 0. There won't be any moment in any of that bracing thing, so it will just take tension. So the section I'm going to take is brace, and that's it. Click here and click here and enter and delete this part. So this is it. This is the model we want for case 3. After introducing this brace element, I am going to analyze this. We already have assigned our load pattern, so I'm just going to analyze it. So go to analyze and go to run analysis, and in here just wind as the action. So wind is going to run. So go to click on run now. So we have a different deformed shape than prior. So we can see the action of bracing. So the deformation uh, this point will be different from case 1 and case 2. So let's check the displacement of this joint, and it is in inch. Yeah, it is in inch, right? The unit in here is inch, so the value is 0.2721. Oh my god, this is the value we want, because according to the problem it says that only a deformation or the deflection of joint D less than 0.48 inches is allowed. So we can see that the displacement of joint D is 0.2721. That's pretty cool. Yeah, the structure is safe by the introduction of this bracing element. So this is what we want. Okay, so to print the data for this case, I'm going to display so tables and joint output. Just uncheck it, click on displacements. Okay, so I need joint displacement, right? So in here select load pattern, it is wind. Okay, load case, it is wind. Okay, and click on okay. Yeah, I'm going to get a table. So for joint 5, the displacement is 0.2721 inch. It is in inch. U1 is along x direction. Okay, yeah, that's pretty cool. And you can copy this to your Excel file and keep it as a result of case 3 to Excel. Okay, done. And if you want to draw the shear force and bending moment diagram for this case, you can do it like I suggested earlier. And okay, we are going to look it once again. So the load case will be wind, and the axial force diagram will look like this. So for bracing, there will be axial force, there will be tensile force in here, and it is 22.68. Yeah, okay. And if I want to look at others like shear, click on OK. Yeah, this is how it's work, and it is pretty cool. Okay, and again to see the moment, click on moment 33. Okay, yeah, this is it. So we can see that in bracing there is just the axial force, neither shear force, neither moment. So the action of bracing uh, reduce the deflection of joint D, and it reduced to a safe limit. And we can conclude that the introduction of 2 by 2 inch square cross section bracing makes the frame stable. Okay.